In this episode, we focus on a deceptively simple privacy engineering idea that has big consequences. Keep different kinds of processing separated so one problem does not become everyone's problem. When systems are small, it is common to put many functions together in one place because it is easier to build and maintain. As systems grow, that convenience can create a dangerous kind of connectedness where data flows freely across features, teams, and tools. In privacy terms, that connectedness increases blast radius, meaning the amount of privacy harm that can happen from a single mistake, misuse, or breach. If everything is tied together, a small leak can expose a broad profile, and a small internal access mistake can become a large privacy incident. Segregating workloads is about designing boundaries so that data used for one purpose stays in the smallest possible zone, and so that failures are contained rather than amplified. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at CIPT-style in the Bare Metal Study Guide series. A good beginner definition is that a processing workload is a specific set of tasks that a system performs on data, such as authentication, payments, customer support, analytics, personalization, or fraud detection. Segregation means these workloads do not all run in the same environment with the same access to raw personal data. Instead, each workload gets its own limited view of data and its own controls, because not every task needs the same level of detail. If you think of a system like a building, segregation is the difference between having separate rooms with locked doors versus one giant open floor where everyone can see everything. The locked doors do not prevent legitimate work, they guide it and constrain it. For privacy, this matters because over-collection, oversharing, and over-access often happen not through a single dramatic decision, but through default convenience, where one team reuses data another team already has. The concept of blast radius is useful because it changes how you evaluate risk. If a system that stores highly sensitive personal data also runs a low-trust workload like experimental analytics code, then a bug or compromise in the low-trust workload can expose the sensitive data. If a developer tool that many people use has access to production identifiers, then a mistake in the tool can leak real customer data into places it does not belong. The same issue appears with third-party integrations, where a vendor tool intended for one narrow purpose can become a gateway to broader data if boundaries are weak. Segregation reduces the chance that an unrelated component becomes a privacy threat. It also reduces the harm if something does go wrong, because fewer systems and fewer datasets are reachable from the point of failure. One of the clearest reasons to segregate workloads is purpose limitation. If a workload exists to provide customer support, it needs information to solve problems, but it may not need marketing attributes or detailed behavioral logs. If a workload exists to analyze system performance, it needs timing and error signals, but it rarely needs personal content or identifiers. If you let every workload tap into a single shared pool of raw data, you are effectively abandoning purpose limitation because the system makes repurposing effortless. Segregation forces you to declare what each workload needs, which encourages minimization. It also makes it easier to explain and defend what you do because you can point to an architecture that reflects your privacy promises. When purpose is reflected in boundaries, the system is less likely to drift into overreach. Another beginner-friendly angle is to think about trust levels. Not all code is equally trustworthy, and not all users of a system should be treated the same. Some workloads are stable, heavily reviewed, and tightly controlled, like payment processing or identity verification. Other workloads are more exploratory, like product analytics, machine learning experimentation, or A/B testing. Exploratory workloads change often, involve many people, and sometimes rely on third-party libraries, which makes them inherently higher risk. Segregation lets you keep high-risk workloads away from sensitive raw data by giving them only de-identified or aggregated inputs. It also allows you to keep experimental outputs from flowing back into core systems without review. The privacy benefit is that you can innovate without putting the most sensitive parts of the system at constant exposure. Segregation also supports the principle of least privilege, but at a system level rather than just a user level. Instead of only limiting which employees can access data, you limit which systems can access which data. A workload that does not need names or emails should not be able to retrieve them, even if a developer accidentally writes code that asks for them. This is a powerful safety net because it reduces reliance on perfect human behavior. It is the difference between telling people not to touch a hot stove and installing a barrier so they cannot touch it by accident. When system boundaries enforce least privilege, privacy becomes more resilient to mistakes. It also becomes easier to audit because access paths are fewer and more predictable. A common privacy failure happens when analytics and core product processing are not separated. If event tracking runs in the same path as core functions, it can end up capturing sensitive values like account identifiers, search text, messages, or form inputs, especially when tracking is implemented quickly. Once captured, those values may flow into multiple downstream tools, including dashboards used widely across a company. Segregation helps by making analytics a separate workload with strict input rules, such as allowing only a controlled set of event types and redacted values. It also encourages the use of stable internal identifiers only where absolutely necessary, rather than spreading them into every telemetry stream. For beginners, the main lesson is that combining analytics with everything else makes accidental surveillance easy. Separating it makes discipline more likely. Another place segregation matters is in environments, especially the gap between production and non-production. Many privacy incidents start when real personal data leaks into test environments, developer laptops, or shared debugging tools. That often happens because workloads are not segregated by environment or because teams copy production data for convenience. A privacy-first approach keeps production processing separated and prevents raw data from being used in less controlled settings. When teams need realistic test conditions, they can use synthetic data or reduced datasets that have been de-identified. The reason this is so important is that non-production environments tend to have weaker access controls and more casual sharing. Segregating workloads includes protecting the boundary between real users and development experimentation. Segregation also helps with incident response because it makes it easier to understand what happened and to limit damage. In a tightly connected system, an incident investigation turns into a wide search across many services and logs because data flows everywhere. In a segmented design, you can focus on the affected workload and the limited datasets it can reach. This makes response faster and reduces the chance of missing hidden data flows. It also helps with notifications and remediation because you can identify which people and which records were in scope. From a beginner perspective, this is a practical payoff. You are not only building for privacy ideals, you are building for manageable failure. Systems that assume failure will happen someday tend to be safer because they prepare for containment. There is also a fairness and trust aspect to segregation because it reduces the chance of internal misuse. If many teams can access broad datasets, someone will eventually use the data for an unapproved purpose, even if they think they are helping. Segregation makes such repurposing harder by default, which encourages proper review when new uses are proposed. It also reduces curiosity-driven browsing because the data is not easily reachable. This is not about assuming bad intent. It is about recognizing that easy access leads to casual use, and casual use leads to privacy erosion over time. When workloads are segregated, new connections become deliberate projects rather than accidental shortcuts. That deliberate friction is often what keeps a system aligned with its stated values. A key misconception is that segregation is only about security, like preventing hackers, but in privacy engineering it is also about controlling meaning and context. Data collected for one context, like support troubleshooting, should not automatically become data for another context, like marketing targeting. When everything is merged, context collapses, and the system begins to treat people as a single profile rather than as a person interacting in different ways. Segregation protects context by keeping data in the smallest zone that matches the original purpose. It also supports transparency because it is easier to explain what happens to data when it does not take unpredictable paths. A system with clear boundaries is more honest because it behaves in a way that matches its explanations. To make segregation work, you need to pair boundaries with disciplined interfaces. Interfaces are the controlled ways data moves between workloads, and they should be narrow, well-defined, and monitored. A workload should not be able to reach into another workload's data store freely. It should request only what it needs through a limited pathway that enforces rules. This helps prevent data sprawl and reduces the chance that one team accidentally exposes more than intended. It also makes it possible to apply privacy controls like redaction, tokenization, or aggregation at the boundary. Even without getting into tools or configurations, the conceptual point is clear. Boundaries without controlled interfaces are just wishful thinking. A defensible architecture shows not only that workloads are separated, but that data movement is intentional and constrained. When you put it all together, segregating processing workloads is a way of building systems that contain privacy harm instead of spreading it. You separate high-trust and high-sensitivity workloads from exploratory and high-change workloads, and you give each workload only the data it truly needs. You keep analytics and experimentation away from raw personal data, and you prevent production data from flowing casually into weaker environments. You use narrow interfaces so data moves only when there is a real purpose, and you reduce opportunities for misuse and misunderstanding. The payoff is that privacy becomes more resilient, incidents become easier to manage, and trust becomes easier to sustain. In privacy engineering, good boundaries are not bureaucracy. They are the architecture that keeps a system's promises from collapsing under its own complexity.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.